name is Luan, and I'm from Facebook. I came from California. And this is my colleague Celeste. And today we're going to be talking about using machine learning for code discovery at Facebook. And this is joint work with Professor Kaushik Sen at UC Berkeley and also our team manager Satish Chandra. So we are part of the team called Big Code at Facebook. And what that means is that our mission is to use a combination of machine learning and software engineering technologies to solve the problems that come up with working with large company code bases. So what are the issues that you can that can come up with working with large code bases? Well, it's actually there's plenty of issues. So things like the first thing that people come up with have problem with is that you just don't know where the code is. There's so much amount of, I think in the keynote, Simon mentioned there's probably order of tens of millions of lines of code at Facebook. And there's a problem of just finding the code where to start. And then once you find where to start, the next thing is that what's the correct thing to use? There's tons of different frameworks here. What's the correct things to call? And what's the correct way of using a certain framework? Well, the fact that we have a big code base is also actually an advantage to us because the benefit of that is that so if you want to ever do something at Facebook, given that there's so much code, chances are there already is some place some code basically does what it does, and you just need a way to find it. So really, this is what the talk is really about. We're trying to build new ways for people to be able to discover code and to be able to exploit on that. So some ways to exploit code bases, including, for example, autocomplete. You can use your code base, the knowledge in there, to inform your autocomplete providers to, for example, rank the methods in the candidate list, and that's being done at some companies. But today we're going to show you two more kind of new approaches that we have developed at Facebook to help people find code. The first is called neural code search, and the second is Aroma. Yeah, so what is neural code search? So neural code search is essentially a code search tool, of course, that accepts natural language queries. So think of it as a system that it indexes on the code corpus, and then you can just ask it questions, things like how do I do this, how do I do that, and it will try their best to find the most relevant code snippets in the code base. So I'm going to talk about why we built this tool, and then I have a demo for you. And then we'll go into the details of how the search model works and how we're evaluating it. Yeah, so the motivation is really easy. I've already kind of said it. The most common question that every developer has is, well, how do I do something? And this is essentially what programming means, because if you can figure out by yourself, then we don't need programmers. And this used to be a very hard problem. It used to involve, reading documentation, asking your colleagues, and trials and errors until we have this website. So Stack Overflow. This is a website where millions of developers are online, and they discuss coding questions and answers. And the nice thing about it is that people actually provide example code that, with some explanation, that does exactly what the person asking the question wants to do. And then most developers have been conditioned such that if they ever see, well, if they Google the problem, and if they ever see a highly voted answer like this, they just don't look further. They don't read more documentation. They just copy paste the code into their program, and usually it does what it does. And the reason is because that these are real world code snippets that people have curated, and they will solve the task at hand. So this is really nice. It shows how one can benefit from just being able to type out the question and then just get the code snippet that one can use to accomplish their own goal. And unfortunately, this is not something that people really get in these large companies for a couple of reasons. For example, although there are open source components, there are a lot of code in our code base that's proprietary, that's specific to Facebook's frameworks. And then it becomes problematic because you cannot really search these things online. That's one. And two, if you, well, so raise of hand, whoever has used the language hack. Right, so that's the point. If you want to search something, well, you can get some answers in Python, in Java, but if you want to hack, then the online search engine doesn't work. But as I said, there's something that does work. We have a big code base, and then we can leverage it because the code you're searching for might be already in there. So this is what neural code search is. It is a search tool, again, that allows people to be able to make natural language queries, ask questions to a code base, and we'll retrieve the code that you want. So let me show you a demo. I should mention this is not a demo on the Facebook codebase, because otherwise I will be fired in the next 5 minutes. But for the demonstration purpose, we have created we collected about 1,000 open source repositories from GitHub. I think they're all in the Android. They're all like Android frameworks. We use this same data set for evaluation purposes. But here's a demo of how it looks like. Yeah, so essentially you type your questions there, and then is this playing? Okay. Yeah, and then you just get your answers like that. You just type in the question, and then the system will return the code snippets that it thinks the best matches your query. So for example, let me try to play this again. So the question here is, I typed in how to close or hide the Android soft keyboard. And then the answers you see, the code snippet you find actually calls the correct API in the Android framework, which is the input method manager, and it will close the keyboard for you. One thing to mention that so this whole method is applicable to an unsupervised, to an unallocated code base, which means that, well, it's nice to have natural language clues in your code base, but we assume that the majority of the code base is not well documented, as there's no like perfect natural language description for every method, but still this is able to retrieve that. So having seen the demo, let's dive into how neural code search works. So overall, there are 2 phases. This is overview. The first phase is we call the model generation phase, where we essentially index the corpus and then create word embeddings, which I will talk more in a bit. And on the bottom is the search retrieval phase, where a query comes in, and I will show you how the system can retrieve the relevant code snippets. So the whole reason that we believe this method works is based on one observation. That is, there's a famous paper called, I think, The Naturalness of Software, where it says is that source code is natural in the sense that people write source code not just for machines to execute, but also for other people to understand. What that means is that means the source code that you see contains meaningful names. People are not just they're not writing binary code. They're naming their things meaningfully. The APIs have their meanings. Their class names have their meanings, and this is where we get the clues of what the program might do. So what this also means is that we're able to treat source code as natural language documents, and we're able to apply these kind of NLP techniques on it. So how exactly do we do that? Well, the first step is actually simple. It's so we index method as a method granularity. So every single method we treat it as a one single searchable document, and then we just extract words from it. So here, this is a just some random Java method, and then we just extract whatever we think are the natural language components in this method. So the method name, all of the method calls, the class names, string literals, and comments. Whatever we can scrape from the method, we put them together. And then the next thing is tokenizing, which means we break up the words. Get resources becomes get and resources. We break them up by a camel case, snake case. We do the common filtering of stop words. And what this step does is that it turns a method in the source code into just a sequence of words on the bottom. And at this point, we just treat it as a natural language document. And once we do that, the next step is to train word embeddings. So for those of you who are not familiar, word embeddings essentially is a function that maps words to a continuous vector in some vector space. Usually n is like 100 or 500. And the benefit of this is that the words that are being used in similar contexts in your corpus are mapped to vectors that are close by in the vector space. And the reason, well, so if we don't do this, then let's say we have 10,000 different words in the vocabulary, then each words are distinct, right? So when you're doing a search, if there's no exact word matches, this is unable to help. But if we're able to map these words into a continuous vector space and have these characteristics of similar words being close together, if you don't have this word, you can have similar vectors, and this will give you sort of the synonym effect. So at this step, we used a open source project at Facebook called FastText to do the training. It is essentially word2vec, for those of you who know, with some optimizations. But the result is, so we trained this using the corpus that we collected from the source code. I know most of the NLP literature, they use a pre-trained embedding corpus, for example, from the whole English Wikipedia to train the words. The reason that we train this thing on our own code base is that we believe some words have different meanings in the code sphere. A classic example is that if you think about it, strings and threads are the same thing in English, but they mean very different things in programs. So just to illustrate what we get from here, once you have these word embeddings, once you map every word to a vector, you can do queries like this. So you pick a word, let's say keyboard, and then you can map it to a vector, right? And then you just search in this vector space, what are the closest neighbors to the word keyboard, and the results you get should be meaningful in the sense that they should be words that are used in a similar context. So here, for example, we get soft. The reason is that in the source code, it's usually the software keyboard, so the soft appears a lot, and then IME, which means the input method editor in Android. So this is nice. The next step is we have word embeddings, but how do we create document embeddings using these word embeddings? Because you need a way to represent the documents in order to do the search. Well, the simple idea is to average them. The problem we find with simple averaging is that if you have a long document, if a document contains a lot of words, the vectors, when you add them together, they sort of lose their meanings. They don't really, you start to not match anything. What we really want is some sort of weighted average, and the method we use is called TF-IDF weighting. It's coming from an information retrieval. It means term frequency, inverse document frequency. So this is essentially a weighted average of each word embedding W. And the weights, what they mean is that, this is a simplified version, but what it means is that term frequency. So the more frequent a word appears in your document, you get a higher weight. And then the more common a word is in the entire corpus, so let's say 50% of all of the document contain this single word, then that's too common and that gets penalized by being on the bottom. So after applying this weighting, what you get is what you get are the most representative words in the document, and they get a highest weight. And then when you average them using this weighted scheme, you tend to retain the semantic meaning of a particular document. So you can apply this on all of the documents, and what you get is that for every method, remember we index this at method granularity. So all of these are mapped to those little dots in the vector space, and you should get this similar effect that if two methods are similar but not identical, they should be very close together in the vector space. So that is the model generation stage. And then by the end of this stage, we get two things. One, we get the word embeddings table, which we can use to encode a word into a vector. And also we have the whole index of document vectors, where each method is represented with one vector. So now what happens when a query comes in? Let's say we have the same natural language question, how do I hide the Android soft keyboard? We do that, we remove some stop words, like how do I, doesn't really mean anything. So we remove those words, and then we map the rest of the words into the vector space using the same word embeddings. So for example here, and then we do I think here we just do the averaging because there are not many words in the question, and then we map the same thing in the same vector space. So you have noticed that here we are relying on the assumption that the question that people ask, the word that you use in there kind of roughly matches in the same vector space as the code space. And then we just so then you have a question vector, you have a lot of document vectors, you just multiply them together, you rank them by the dot product or cosine similarity, and then you just surface those that has the most cosine similarities. So in here what you get are things like, so for example here, close hide the Android keyboard, you get two things that don't necessarily correspond to the question exactly, like word-to-word match, they're not that, but they have enough words overlap and also the effect that we get from having these synonyms that they retrieve the correct method. So the assumption is that if a programmer has trouble, implementing how do I hide the keyboard, they see these two code snippets, it's able to help them at least point them in the right direction or even reuse these methods. So that's the search model, and I'm going to briefly talk about how we evaluate this. Because this is not trivial because it's very hard to come up with a set of benchmark in our own code base saying that for these questions you should get these code as answers. So what we do is that we turn back to Stack Overflow and then we use them as the ground truth. So for a question and answer like this, we just take the title as a question. We assume someone asks, how do I hide the keyboard like that? And then we assume the target answer. We have some filtering criteria, but in the end we have some of the highly voted answers. We assume them to be the ground truth for answering this question. So for example, here we assume this code snippet is the code that you should write if you wanna hide the keyboard. So we're able to curate basically a benchmark data set for these. And then for evaluation, as I mentioned, we took another set of open source repositories in the Android domain. And so again, this is unannotated. So we just put NCS, we just train NCS neural code search on this data set. And then we hope that it will answer the questions in the other data set. We have some kind of preliminary filtering criteria to make sure that the answers that we're looking for actually exist in this code base, but we're not 100% sure. So in the end, we just manually went through 100 questions. So for each question, you pass it through NCS, you get a bunch of code results from the GitHub repositories, and then we did a manual comparison to see if any of the results actually make sense, actually correspond to the questions, to the answers. We later did a larger scale automated study, but you can find that more in the paper. I'll show in the end. So for this 100 data set, the results are actually not bad. For 41 of the 100, we essentially, so as long as neural code search returns a close snippet in the top 10 results that essentially matches the ground truth, we consider it to be successful. So in 43 questions, neural code search is actually able to answer the questions posed in Stack Overflow questions. In 8 cases, it's almost correct in the sense that it points to at least some of the right APIs. It might not have the correct flags set, but it can still be helpful. In the other 49 cases, it's not returning the correct things. So to interpret the results a little bit, some of the questions, well, most of the questions that the neural code search is able to answer correctly are those that, in the sense, more literal in the source code itself. For example, these questions are a little more specific. How do you convert from bitmap to drawable? How to find the MAC address? How to handle the back button? They have some keywords that pinpoints to those code that calls these methods. For other more complicated code structures, they are, for example, in Java, there are like threads and actors. They require code across methods. We don't handle that now, so that constitutes the other half of the results. So just to sum up, neural code search, it enables natural language code search on code. It combines word embeddings from NLP and TF-ATF weighting from search engines. It does not require annotated code corpus, and then it is fast and easy to deploy. So I guess I can take questions for neural code search, or we can have questions afterwards. Do you guys have any immediate questions? Yes.
So the question is, I noticed you were using, you're scraping comments from the code as well as like Reranking and stuff. Have you done any experiments to see if you don't have that level of comments, or if you don't scrape the comments, are you still getting a good signal in terms of like what terms people are using and stuff like that, or are the comments really necessary?
Right. So the question is, thank you. The question is have we tried how important are comments in this search engine? Have you tried not using comments? We haven't done any formal studies, but from just our experience, comments are not that popular in source code. Most of the source code that we scrape don't have comments or don't have good documentations at all. So well, I mean, we definitely want them. They couldn't hurt, but the reality is that we don't have that much in the corpus. Yes.
What about timestamps? Does that factor into the relevance of what you're looking for?
The question is, does timestamp factor into? You mean like in terms of ranking the results?
So how recently something was in the code base?
Yeah. So I guess the question is, do we rank results, or do we consider the recency of code in here? We don't right now, by taking the assumption that the code that we have, like in the instance that we deploy this at Facebook, we assume that the code running in production are essentially correct. That's not necessarily true for when you collect a large sample of open source corpus, and as we later find out, that's also not true in our own code. Because people evolve code, people deprecate stuff all the time, but that's something we're looking for. That could factor into ranking. All right, I'm going to hand off to Celeste now because we have another project to talk about.
Hi, I'm Celeste. I'm going to talk about another project of the Big Code team called Aroma. So Aroma is a code recommendation tool that takes a short code snippet as a query. I'm going to first talk about why we built this tool, show you a demo of how it works, and then I'll get into the technical details and our evaluation of how well it works. So Frank just explained how neural code search can help answer the question, how do I do something, by searching code in a big code base using natural language queries. So imagine you're an Android developer at Facebook and you've just used neural code search to figure out how to load a bitmap image. So you came up with this line of code that calls the bitmap factory.decodeStream method to load a bitmap from a file. And so then maybe you think, great, I'm done, that was easy. But then you remember that you're coding in a production environment, so your code can run on millions of devices. So you really want to make sure that your code does what it's supposed to do and won't crash on people's phones. Often this can mean adding additional code for safety checks, error handling, etc. In other words, you want to know, is there anything else I should add? Well, what if other programmers have already written code similar to this? Could you use their code to help you? And in fact, is it often the case that the code you write has meaningful similarities to code already existing in a large code base? Well, we did an experiment to answer this question where we looked at newly written code and tested how similar it is to existing code in a large corpus. We found that for a little over a third of cases, new code contains meaningful structural similarities to existing code. And we think this similar code has a lot of potential to save developers time and effort. We could use this similar code to fix bugs, find useful APIs, and figure out what additional code should be added. But locating this similar code can be challenging, and the larger the code base, the more challenging it becomes. And this is where Aroma comes in. So I'll now show a demo of how a developer may use Aroma. As with neural code search, this demo won't show real Facebook code, and it's instead a corpus of open source GitHub projects. So say you're writing this code and you're not sure if it's correct or if there's anything else you should add. So you decide you want to reference similar code that other developers have written. So you highlight your code, press Command ? And then Aroma will load a short list of recommendations for you to look at. These recommendations are synthetic code that are created by clustering together similar methods in the corpus. So by looking at these recommendations, you may figure out what code you want to add. So now let's take a closer look at the code these recommendations actually contain. So this is the first recommendation. Here, Aroma has found 5 methods that not only call the decode stream method, but also pass in additional options that set the sample size. This is an important configuration that will reduce the memory consumption when decoding large bitmaps, and Aroma has found 5 places where this configuration exists. This is another code recommendation. This time, Aroma found 6 recommendations that contain code about input stream, indicating that it's idiomatic to close the stream after use. This is something else we could add to avoid leaking any resources. And here's a third recommendation. This try-catch block is found in a cluster of 4 methods. It handles a potential I/O exception that could arise when loading the bitmap. Although this code might run smoothly on the Android simulator, in real-world scenarios, we don't want our app to crash if some file fails to open, so this could be another important thing to add. So those are some examples of the kinds of recommendations Aroma offers, and now we can take a closer look at how Aroma creates these recommendations. So our problem statement is that we have a large corpus of code and a query code statement. In our case, we have a corpus of over 5,000 GitHub Java Android projects containing over 2 million methods. Our goal is to find all code similar to the query and use the similar code to generate a short list of representative extensions to the query. We call these extensions code recommendations. So Aroma is based on 3 key ideas, the first being feature-based search. Here, we want to narrow down the millions of methods in our corpus to the 1,000 methods that have the most overlap with the query code. And we need to do this fast so it's actually usable. So to better demonstrate how this feature-based search works, I'm going to reference this example query code snippet on the left. What we want to do here is extract features from the query code that offer structural information about this code and use those features to construct a vector. So the next question is, how do we extract features from this code? Well, the first step is to parse the source code to get a simplified parse tree. Here, the keyword tokens are circled and the variables are double circled. We use this parse tree representation because it can be used uniformly across different programming languages. So to implement Aroma for a new language, we only have to write a new parser. We now extract features from the parse tree. There are 4 kinds of features that we extract. The first are token features. Basically, for each token in the tree, we create 1 feature. One thing to note here is that variable names are replaced with the #var label that you can see as the first feature in the list. We ignore variable names because we consider a query code snippet and a code recommendation to be similar, even if they differ with respect to the renaming of variables. For instance, if a method contained the code in our query snippet, except the variable was named j instead of I, we would consider that to be an exact match. The second kind of features we extract are parent features. Here, for each token, we add a feature for its parent, grandparent, and great-grandparent, and we create the features by concatenating the name of the token with the name of its parent, with the number denoting which child the token is of that parent. Here's an example of parent features created from a different token. These features help to capture some of the structural properties of a code snippet. Sibling features are the third kind of feature. Here for each token, we add features for the previous token in the tree and the next token in the tree. These further help capture the context of the tokens. The final kind of features we extract are variable usage features. Since we abstract out the variable names, we want a way to connect the usage of variables. For instance, if we declare a variable and then use it in a condition, we want to capture that with a feature. So for each variable token, we add features for its previous use and its next use. So this is how we extract features from a code snippet. We do this feature extraction process on every method in the code base and make a set of all features found across the code base. We then construct a vector for our query code whose length is equal to the total number of features, and each entry in the vector is equal to 1 if that feature is present and 0 if it is not. So this gives us a vector representing our query code snippet. We also do this vectorization process for each method body in the corpus, which forms a matrix. We multiply the matrix with the query feature vector and get a dot product vector. Then we pick the top scores to get the methods that contain the most overlapping features in the query. And this is what we want out of this step, methods that most overlap with the query. There are over tens of millions of features in total, but each query or method body will only contain a couple dozen features at most, so the vectors are very sparse. And this makes this step very fast. It takes less than 1 second for the over 2 million methods in the corpus. So now we have a relatively short list of methods from this feature-based search, and the next step is to re-rank and cluster these methods. Re-ranking is important because given the query on the right, the method on the left may be one of the top search results. But we need to figure out how much of the query code is contained within the method, not just how much overlap there is between the two. For instance, we want to be able to identify this part of the method as the measure of overlap from phase 1 is only an approximate measure of similarity. To do this, we need to define a more precise measure of similarity, and we do that by defining a similarity score. So this equation defines a similarity score between a query code snippet Q and a method M. The key here is that we prune the method by finding the subset of M that maximizes the similarity score. And this gives us our more precise measure of similarity. We calculate the similarity scores for each method in this list and re-rank based on that. And this gives us a more accurate list of which methods are the most similar to our query code snippet. But that would still be a lot of similar code to look through, and many of those methods contain similarities to each other. So the next step is to cluster. We cluster using a greedy clustering algorithm where we start with each method in its own singleton cluster. And at every iteration for each cluster, we find the best snippet to add to this cluster. Best is defined as similar to existing snippets in the cluster and sufficiently larger than the query code snippet, as the goal here is to create extensions to our query code that will be the recommendations. We iterate until all clusters stop changing, and then we get rid of similar looking clusters, which is defined as having a Jacquard similarity of greater than 0.5. So now we have just a few clusters of methods containing similar code. The next step is to intersect the methods in each cluster to create a representative code snippet. I'm going to show a little video demonstrating how the intersection process works. So we start with the first method in the cluster, and we compare it against every other method. And each time we prune out lines of code that are unique to one method and preserve lines that are common to multiple methods. And when we've done that for the full cluster, we have our code recommendation. So now that we've seen how to use Aroma and how it works, I'm going to talk about how well it actually works in practice, and talk about one of the experiments we did to figure that out. So as with neural code search, we reference Stack Overflow to evaluate Aroma. So for this experiment, we picked the 500 most popular questions on Stack Overflow with the Android tag and looked at the top voted answers. And from each answer, we extracted Java code snippets that had at least 3 tokens, 1 method call, and fewer than 20 lines of code. And we randomly picked 64 Java code snippets from this set. This is an example of one of the 64 code snippets we took from Stack Overflow, which shows how to hide a soft keyboard in Android. For each of these code snippets, we manually created an Aroma query from the first half of the snippet. For instance, this is the query we extracted from this code snippet. Since each full code snippet from Stack Overflow represents a full popular coding pattern, the goal of this experiment was to see whether Aroma could recommend the missing statements in the code snippet given the partial query. We couldn't extract queries from 14 of the 64 code snippets because they contained a single statement, but for the remaining 50 code snippets, Aroma recommendations fall into one of 2 categories. So in 74% of cases, one of the top 5 Aroma recommendations matched the original code snippet, while in the other 26% of cases, none of the Aroma recommended code snippets matched the original snippet, and instead offered some alternative recommendation for the partial code snippet. Above is the code snippet from Stack Overflow we were just looking at, and below is the Aroma recommendation given that query from the original code snippet. Here, the highlighted line matches the query, and the code above and below the highlighted line is the recommended code from a cluster of 3 methods. In this case, the recommended code passes the current focuses window into the hide soft input from window function, which is an exact match to the original code snippet. In addition, we ran Aroma searches using each of the 64 full code snippets as queries to test if Aroma would add any additional useful extensions to these coding patterns. And we found that the code recommendations fell into the following 5 categories. The first 4 categories describe important extensions to query code that could improve the quality of the code. And the final category describes the cases where the methods matching the query snippet were mostly different for each other, so Aroma was unable to perform the clustering and intersection steps. So to offer some takeaways, we found that about a third of new code contains meaningful similarities to code that already exists. And Aroma aims to help developers identify and utilize the similar code. And our experiment found that Aroma can provide exact recommendations for 74% of Stack Overflow questions. So here are some links to our papers and blogs if you want to check them out. I also want to plug another talk from the Big Code team about Getafix, which is an automated bug fixing tool, which will be tomorrow at the same time and place. And I'll also shout out our other people working on this project who are not here today. And now we can take questions on Aroma or more questions for neural code search.
Yes.
You mentioned something about space to talk about containment of snippets, and then you showed some formula with the subsets. Could you just quickly explain how those two relate?
Yeah.
I'll repeat the question. The question is on phase 2 of the Aroma, I think the re-ranking and the clustering stage.
Next
I think the one with the formula. This one? Yeah, what the similarity means.
Oh, so f of q is the set of features of the query, and m prime is the subset, is like a subset of the features of m. And so basically we're taking all the features that are common to both the query and the pruned method, and dividing that by the total features that are in both the query and the method.
I think something to add or to make this more intuitive is that the first step we created with the one-hot vectors. That's a fast way of reducing the candidate set to a small number of methods. It's not precise in that it does not tell exactly where in this here. So where in this? So you could match a very long method on the left-hand side which contains all the features that you want, but we need this kind of precision neural net to pinpoint where exactly these code matches and what are the surrounding code in order to create the recommendations. Hope that helps. Yes.
To be an improvement, you don't have to be perfect, just be what people do now, which is mostly ask people who've worked on the code base for longer. Have you scored your tools against asking, against human performance in this area?
So the question, I think, is about Aroma. So Aroma essentially provides recommendations to your existing code by telling you what other people have done. Have we compared this with actually asking experts to improve the code at hand? Well, we didn't do that, but we did do a user study where we tried to give people some programming tasks, and so in the control group we don't let them use Aroma. In the experiment group we let them use Aroma to see if they are actually benefiting from seeing these code recommendations, and the short answer is yes. Yes. So could using Aroma result in duplicate code? Yeah, so yeah, we don't want to. The reality is, well, so we don't want to in that we don't want people write exactly clones of methods. In reality, that's code clones are not that easy to avoid entirely because mostly because of dependency issues. You have different parts of the code base that sometimes it makes sense to refactor out the method, put in the utility class, and in many times we do that. But in other cases, let's say from some backend Java code, you find something you want to put in your Android app. That's not so easy to refactor. So this does. It's possible to introduce duplicate code, but in the meantime, we're hoping we're also promoting the best practices. So at least you're duplicating the good code.
Related to that, what happens if you run Aroma on a code base where there's no duplicate code? Does it still function?
So the question is, what happens if we run Aroma on the code base without any duplicate code? I think it depends on how you define code duplication. For example, in the example where we get the system service of the input method, that line of code, that line of code will be duplicated, although the things afterwards might be different. I think Aroma is based on the premise that there are certain idiomatic ways that people use a certain service or certain API. They might differ in the details, but Aroma is designed to tolerate these kind of small details while still surfacing these kind of common patterns. So at least in our use cases, it functions well.